This talk was formerly known as Gordon's Secret Session. If you don't know what or who Gordon is, that's our pet turtle in the HQ in San Francisco. If you ever visit San Francisco, you can visit the HQ and you can visit Gordon the turtle, who was that size when I joined. And by the time you show up there, the Gordon might try to eat you and even be successful at it, so be careful. So this last session will be about Kubernetes in Docker, and we have two of the folks who worked on that during the last few weeks and months. This is the only session that I wasn't given the privilege to review before because it was a secret, or maybe these fine folks were also working on the keynotes and had no time for a rehearsal for that session. In any way, one thing I wanted to mention is that they will kind of handpick a few areas to put spotlight on. But we have a large fraction of the Docker and Kube team here in the room. So if you have extra questions, stuff that you want to know about, then just stick around by the end and we can find answers to all your questions as long as there is Kube and Docker in the question. Please, a warm applause for Alex and David.
Thank you. I'll grab the first part.
All right. Thank you. Hello, everyone. So I'm Alex. I'm an engineer in the Docker Enterprise Edition team.
I'm Daniel as well. Also work on the Enterprise Edition team.
And we'll be talking about the integration of Kubernetes in the Docker platform.
All right. So what are we going to talk about? So first, what we're going to do is give kind of a quick recap of the demo that we gave at the keynote. But we're actually going to throw some bonus features in that we didn't have time to show off during the keynote to show some of the other capabilities of the platform. Then we're going to go into kind of general architecture for both CE and EE and how Kubernetes has been integrated. Talk about kind of the major moving parts and how those pieces fit together. Then we're going to drill in a little bit more on some specific EE areas that we think are interesting for folks. So the first one we're going to hit on is topics around mixed workloads. So those are workloads that are mixed between the different orchestrators in the system. And then we're going to also go deep into authentication and authorization and how that's been wired into the system. We want to try to leave a good chunk of time at the end for QA. And as Jerome mentioned, we're also the last track, so we can stick around a little bit later if necessary if you guys have a lot of questions. So let's go ahead and get running. All right, so first, let's go do a demo. Let's pop out here. And I'm going to let Alex drive.
All right, so here you can see our dashboard. We have both Swarm and Kubernetes workloads running and all of our nodes here. Let's go ahead and deploy compose file. Again, stacks are a shared resource now, so you can deploy either Swarm services, basic containers, or Kubernetes workloads using a compose file. I'm going to upload a compose file. This is the same demo we saw on the keynote. It will launch a three-tier application with a web front end, a worker, which will generate random words for us, and a database. So I'm going to name that. Let's call it stack1, very genuine, and put in the default namespace. Now, namespaces in Kubernetes is where all resources have to belong in a namespace. The reason for that is they provide the virtual multi-tenancy, so the resources in one namespace cannot be used in another namespace. For example, if you have a secret in namespace A, you cannot use it with a pod in namespace B. But for now, these all need to be together, and we don't have any external dependencies, so we'll just choose namespace default. So let's go ahead and create that. Now, if we select this stack that we created, we can see the full compose spec here on the inspect pane. And we can track the status of our stack, which is currently in a starting state.
So one thing I'll mention real quick, as Alex was just showing, the compose file actually embedded in there. So one of the features people have been asking for a while in an enterprise product is the ability to actually do full round trip and lifecycle of those compose files. Mm-hmm. So this is one of the nice characteristics that we get with this new implementation, is the compose file is now actually persisted in the system, and you can actually do round tripping. So we'll show that in a moment.
Let me show you. So if we go to controllers, we'll see the actual Kubernetes controllers that were deployed as part of the translation of the stack format into native Kubernetes controllers. In this case, our three tiers became 3 deployments, and each one of these deployments had a replica set mapped to it. And let's go ahead and edit that compose file, as Daniel said. We'll go back to stacks, find it here. we go to configure, we can now edit it. So, well,
So you got the full compose file, change settings, round trip, bring it back into the system.
So I'm going to turn it up to 11. All right. So if we go to controllers, we'll see that now we have 11 pods there. So that's how you can edit a stack and change its configuration, change its desired set of state, and so on. The other resource that is created as part of the translation of a stack is services. In Kubernetes, services are a routing construct. So in this case, the web service is the one mapping to our front end, which is exposed using the node port method, which is why we have a URL that allows us to access our service in the end. So let's move to pods. Pods are the fundamental scheduling unit in Kubernetes. Everything is actually created as pods. And I'm going to talk more about pods in a minute. And yeah, you can actually create native Kubernetes resources through the UI. In the keynote demo, we only showed it through the command line interface. So let me quickly show you how we can create the same job file. It's a Kubernetes batch job. We'll put it in the default namespace again and can create it, and it gets created in the same screen. In this case, you may notice that pods is 0 out of, well, TAC. The reason for that is because the desired state for a job is for the pods to complete once successfully. And you can see that it was completed. And if we go actually to pods, we can see that we just ran that pod and was successfully succeeded in its state. So one last thing we didn't fully explore in the keynote demo is how to use the client certificate bundle feature. Every user is able to go to their own profile page in Docker Enterprise Edition and click this new client bundle icon, and that will download a zip file. Now what that does is if I unzip that, you'll see there's a set of certs. Those are client certificates that represent the user. The username of the user is the issuer common name of the certificate. And there's also a script here, which what it does is it sets 3 environment variables that configure your Docker command line tool to point to what we call the UCP controller. It's the main API entry point for Docker Enterprise Edition. And there's also a set of Kubernetes command line tool commands that will do the same for the kubectl tool, and it will tell it to use client certificates for authentication. So I'm going to go ahead and source that file, and if we do, let me clear the screen. If we do docker node ls, we'll see that Swarm can see the same set of nodes, and kubectl kit nodes. Kubernetes can see the same sets of nodes as well. So one last thing is, if we get the full list of pods that are currently in our default namespace, we're actually able to use both tools to complement their functionalities. So in this case, if I wanted to use a Docker tool against containers created as part of the specific pod, the first awards pod, I could do a Docker PS with a filter for name equals its name. That will give us 2 containers. The reason for that is that each Kubernetes pod has what is called a pause container. Now the pause container is used to reserve namespaces and C groups for the entire pod and all of the containers that are going to be part of that pod. So it's always there when Docker's container runtime. So we're going to take the actual container that we ran, which is the Java application, and we're going to do just a normal Docker exec command to it. And we can see the Java process running. But in this case, we went through it through the Docker command line tool, as we had both the Docker and Kubernetes command line tools pointing to the same cluster. So that concludes the demo.
Cool.
How do I go to full screen?
Here, I'll get it.
PowerPoint.
Okay, so now let's talk a little bit more about the architecture. So first, let's go in a little bit about how CE is wired up, and then we'll talk a bit more in depth about how EE is wired up. So CE first. Okay, so underneath, at the bare metal level, we're leveraging the hypervisors on the native platforms in Windows and Mac. So we're using HyperKit and Hyper-V. And because of the way that Linux Kit is wired up and the way that we take advantage of the native hypervisors, we have the capability of doing host file system mounts. So this is extremely powerful from a developer standpoint, and that now you can access all of the files on your host file system, use your text editors, your code editors, your coding environments from your host, mount those into your test containers that you're running both in Swarm and in Kubernetes inside of this Linux Kit VM. So that's extremely powerful. One of the other characteristics that we have of kind of the base platform is something called VPN Kit. And so what VPN Kit does, or allows us to do, is to wire the network from inside of the VM back to the host. And so when you spin up a workload inside of the VM, if it's exposing a port, that will actually show up on your host as localhost. So it's very powerful to be able to point your browser at it or your local tools from your developer environment and see the workloads running inside. Again, both Kubernetes and Swarm. It also means that any workloads running inside the system, when they need to get out to the outbound network, they are transiting through your host. So if you need to use a VPN externally to get back to your back office or wherever your development environment is back at home, that means the workloads running inside of your VM, inside of the Docker containers and Kubernetes pods, are able to actually transit through that outbound VPN as well. So it should make it a much smoother experience for developers. All right, so within that VM, let's kind of work our way up the stack. There is a single Docker engine, and by default, it does not have Swarm mode initialized, but you can initialize Swarm mode if you choose. It also does not have Kubernetes initialized, and you can choose to initialize it if you want. So for the Kubernetes component, it's running as a container. We're using the Hyperkube image to try to minimize the disk footprint and the amount of size and space that we're using for download. But ultimately, we're running the images as containers. We manage the lifecycle of that using the kubeadm project. And so that kind of manages spinning up and managing those containers inside. And as David demoed and Alex demoed, we're using the custom resource definitions to add the capability of stacks. So this is kind of the standard way of extending Kubernetes to add new constructs or new features into Kubernetes. And so that stacks CRD ends up spinning up there. So that allows us to now do Docker stack deploy and actually target Kubernetes. And you can also use the Kubernetes CLIs directly against the APIs as well. All right, cool. I think that's good on CE. All right, so Alex is going to take us through and talk a little bit more about the orchestrators involved in the EE product.
Yeah, so, well, let's first talk about what an orchestrator is. So at a very high level, an orchestrator is an application or a program that when it is a container orchestrator, it uses the Docker API or the API of some other container runtime to create containers natively. And that it's usually its only interface with the environment of how the containers operate. It very rarely has to actually manipulate C groups or namespaces itself. So we use several orchestrators in the Docker Enterprise Edition stack, the first one of which is Docker Swarm. Now, this is the first orchestrator developed by Docker, and it lives on the Docker Swarm GitHub repository. It serves a cluster-wide imperative API, which is based on the single node API of the Docker engine. That means that if you are to do a Docker run operation against Docker Swarm, you're going to get one container deployed on one of your nodes, which is the same experience you would get with a single Docker engine. The reason why this is an imperative API is because you effectively tell the orchestrator to do a specific operation once, rather than defining a desired state for your workloads. You can also track your resources across the entire cluster. So if you say Docker PS, you're going to be able to see all your containers in the cluster. If you say Docker volume ls, you'll be able to see all the volumes that you have in the cluster, and so on. There's a pluggable discovery backend in Docker Swarm, which is used for high availability between multiple manager nodes and for pure discovery of new nodes. And the most commonly used backends there are etcd and console. And using that backend, there's a leader election mechanism under which one of the managers is determined to be the leader. And that leader is responsible for caching the state of the cluster. So it knows in memory what all the containers are, what all the volumes are, and what all the networks are in your system, and their latest state. And based on that cache, Docker Swarm performs scheduling decisions by knowing the exact resource reservations and limits of all of the Docker containers that are running on your cluster. So it would know that, for example, a specific node has containers scheduled that bring that node almost at capacity if you sum up all the reservations, and would refrain from creating more containers on that node. The next orchestrator is Docker Engine with Swarm mode enabled. Now that is the orchestrator that lives on the Docker SwarmKit repository. It features declarative state through the service construct. That means you can go ahead and create a service, and that service can have a determined number of desired replicas and a desired configuration, a desired image, and the orchestrator itself will reconcile the current state of the system so that this service reaches its desired state. That means that if you have 0 of these containers running, it will start spinning containers up. If for some reason you have more, it will start spinning them down. And that's also a way that you can use to do rolling updates for your service. It features a built-in routing mesh and overlay networking. And its scheduling decisions are based on the reservation of all Swarm services that have been deployed across all nodes of the cluster. It also has a built-in raft store where all the state is held, and that raft store is kept in memory, but is also persisted to disk. That raft store is also what determines which nodes are managers and what the raft quorum is between all the manager nodes. And the raft store itself is used to establish a distributed certificate authority, which is how certificates are created to establish per node cryptographic node identity, which is then used to encrypt all communications using mutual TLS authentication. And finally, the third orchestrator that is being added right now is Kubernetes. The fundamental scheduling unit in Kubernetes is pods, which are groups of containers that share the same C groups and namespaces. That means that the processes in these containers behave as if they're in the same node, so they can access each other through localhost, for example. Kubernetes also has declarative state through its notion of controllers. It means that you can create a deployment or a replica set or a daemon set or other controllers, and Kubernetes will reconcile the state of the system to make sure that these pods are in the state defined in that controller. Kubernetes has a flat networking model, which means that there's one IP assigned to each pod, and that model is assigned is delegated to external plugins. That means that you can use a plugin which is responsible for assigning that IP and for making sure that that IP is routable from all other pods in the system. Finally, Kubernetes makes its scheduling decisions based on reservations to limits of workloads in the system. It only tracks Kubernetes workloads, however, does not look at other processes that may be running on the same host. And it also, in contrast with the previous orchestrators, it also takes into account the usage of resources on the system using a tool called cAdvisor that's built into the node agent of Kubernetes called a kubelet. And that tool actually monitors the usage of all the individual C groups of the containers created by Kubernetes itself.
Cool. Thanks, Alex. All right, so let me kind of quickly walk us through the architecture of the EE platform and kind of the major moving parts inside of that. So at the bottom, we start with the Docker Enterprise engine. So all of your nodes in your cluster are running Docker EE as the base engine, or the Docker EE engine, I should say. Sitting on top of that is the kind of the EE stack, and all of these components are generally running as containers, with the exception of Swarm mode. Swarm mode is kind of built into the engine, and you turn it on or you turn it off. Swarm mode is enabled when the universal control plane and when the full EE stack is up and running. As Alex mentioned, we also have the Docker Swarm orchestrator, and now we have the Kubernetes orchestrator as well. So for both Docker Swarm and Kubernetes, they're using the same underlying etcd instance, which is highly available based on the setup that you have in your cluster. So let's talk a little bit about cluster lifecycle, right? So you use the Docker Swarm join command and Docker Swarm node promote to manage whether or not your nodes are managers or there are workers. If the node is a manager, it's going to be running all of the management components of the stack for Swarm mode, Docker Swarm, and Kubernetes. If that node is not a manager, then it will only be running the components necessary to run workloads on that system. To manage that lifecycle, we have a component called the agent in our reconciler, and so that manages both those promotion and demotion flows, as well as certificate certificate renewal, and deals with patching and upgrading. So as you upgrade the system, it will deal with swapping out the appropriate images for these containers that are running on the system. In order to integrate with Kubernetes and support authentication, we've built an OpenID Connect provider. Alex is going to go into a little bit more detail later on how the Auth-N and Auth-Z flows work. But in essence, we've used the kind of standard pluggable interfaces in Kubernetes to wire in authentication into the EE stack. And lastly, just talk quickly about the CA. So as Swarm Mode and SwarmKit are designed, they have a central certificate authority that manages all the certificates and cryptographic node identity of the cluster. We leverage that throughout the stack, so all of the components are using mutual TLS to communicate, and they're using the nodes that are issued by that certificate authority. Let's see. Okay, talk about the top level components. So we've got our graphical user interface that sits on top using the standard Docker APIs and Kubernetes APIs. We've also got the trusted registry, which is what implements many of the secure supply chain features of the platform. We've got the existing Docker CLI, which speaks the Docker API, and now we have support for the Kubernetes CLIs as well. We are using an unmodified version of Kubernetes. The plan is to use version 1.8 when we go live with this next version. And our plan, I'll get my notes here. We are planning to submit the product and aim to pass the certified Kubernetes conformance program. So we intend to be a completely conformant implementation by the time the product goes out the door. Okay. Okay, so let's talk a little bit about plugins and extensibility, particularly on the Kubernetes side. In general, if you have a plugin or an extension that is using the standard APIs for Kubernetes, it should work. The exception to that is if you need to modify the API server or the kubelet flags. So at least in this first version of the product, those flags to those two components will be fixed and managed by the core platform. But if all of the extensions that you're adding are kind of adding in through standard APIs and standard extension points, then those should work. We are going to be looking at, in a future version to extend or to add to the extensibility to allow some of those flags to be modified. From a networking standpoint, we're going to have a built-in kind of batteries included CNI plugin for networking. We are still evaluating exactly which CNI plugin we're going to ship with in the final product. But the goal is to allow customers to choose an alternate CNI plugin if they choose at an install time. So you'll be able to swap out that batteries included version and bring on your own CNI plugin. For ingress, for the layer 7 routing for Kubernetes workloads, we'll also have a built-in version, and you'll be able to swap that out with your own choice if you choose to use a different one. All right, so from a storage standpoint, we have the Docker Volumes plugins that exist today that customers are using and that we have partners that have built to support various storage backends. Our plan is to build a Flex Volume driver that will adapt to those underlying Docker Volume plugins, so you'll be able to access the same storage volumes. There is a project upstream in Kubernetes that's ongoing right now called CSI, which is looking to build a richer plugin model for storage. As that matures, we will look to adopt that in the platform as well. And lastly, for metrics, you can leverage Heapster, which is a standard project out there in the Kubernetes ecosystem, and choose which storage backend you want to use. Or you can roll your own Prometheus or deploy your own Prometheus and scrape the existing API endpoints in the platform.
All right, let's touch on some topics regarding mixed workloads. So the first one of which is resource contention, specifically what happens when we have multiple orchestrators operating on the same nodes. To get there, let's first talk about what it means to have allocatable resources. The set of allocatable resources is the set of CPU and memory that are perceived to be available for scheduling by an orchestrator. When you have multiple orchestrators operating on the same node, that means that you have different definitions of which resources are allocatable in node at the same time. So for Docker Swarm itself is respectful of CPU and memory limits, but the container cache that it uses to determine the allocatable set of resources may be stale after a while, or it may momentarily be stale. For Docker Engine with Swarm mode, it's only aware of its own reservations through the services construct, so other processes running on the same node may occupy resources that are not part of the calculation of the set of allocatable resources. And for Kubernetes, even though it has a very effective way of handling out-of-resource situations through eviction policies and quality of service tiers, that only applies for Kubernetes workloads. It will still not actively monitor the usage of workloads that are not in pods. So because of that, nodes can go ahead and schedule over each other and actually bring a node under to its capacity or near its capacity. When that happens, all CPU shares that have been issued to individual containers can be equally throttled, And the operating system can trigger the out-of-memory killer, which is a process that comes up when the node is near memory capacity and starts killing processes that consume too much memory. The calculation for which processes are killed is not perfect, and even though there's a flag called the adjust score flag that you can use to tweak which ones of your containers have priorities over others for the killer, this is still an imperfect process, and there's other factors in this equation that might affect that decision by the killer. All of the orchestrators will definitely reschedule on an but that means there's potential interruption for workloads, and existing sessions might be terminated while workloads are being restarted. It depends on how highly available their workloads themselves are. And because of that, for production workloads in Docker EE, we'll be recommending using only one orchestrator per node to provision workloads. We're actively working on providing UX primitives to have a setting for each individual node, which would allow administrators and operators to select which orchestrators would be permitted for use on specific nodes. And for example, you'll be able to say, I want this one specific node to run Swarm workloads or Kubernetes workloads or mixed workloads, in which case you would also see a warning pointing to an appropriate article with more details on that subject. In the future, we're planning to work with the upstream of all of these three orchestrators to address their individual shortcomings and to make them more aware of each other so that there's better support for mixed orchestration on the same sets of nodes.
Cool. Thanks, Alex. All right, so let's talk a little bit more about workload interoperability. Kind of two other topics that I think are interesting to talk about is networking and storage. So specifically on networking, we are not planning to tie the layer 3 networking together between the orchestrators. So what that basically means is your Kubernetes pods and your Swarm services will not share that same IP subnet, and they will not be talking directly together at the IP level. What we will do, or what we are recommending, is using layer 7 as the bridge point between your workloads if you have a stack that needs to talk between Swarm and Kubernetes workloads. So there'll be a battery, as I mentioned earlier, there'll be a batteries included Kubernetes ingress controller, again, which you can swap out if you choose to use a different one. There is also a built-in layer 7 routing capability for Swarm services in the platform. You can also use your own external load balancers if you choose for Swarm services. Ultimately, what you would end up doing is configuring external DNS to map to those applications so that they would be visible and routing through the appropriate ingress for them. So give a concrete example. You have a Swarm service that wants to talk to some Kubernetes service or application. It would do a DNS lookup on the name of that application. It would find the IP address of the ingress controller for Kubernetes. It would then route through that ingress controller and do the normal layer 7 routing through the Kubernetes networking stack. Vice versa, Kubernetes workload would do a DNS lookup. It would find the host name, it would find the IP address of the layer 7 routing for Swarm, and it would route through that using the host name to land on the appropriate Swarm tasks. All right, storage. We talked a little earlier about flex volumes. So our plan is to leverage a flex volume plugin that will support Docker volumes as well. So any third-party or built-in storage volumes inside of Docker will be accessible, and you'll be able to mount those inside of your Kubernetes workloads as well as your Swarm workloads. So you'll have storage interop at that level.
All right, so let's touch on how we're planning to implement authentication and authorization with Kubernetes operations. So this lovely diagram is pretty much the entire flow of how a request for Kubernetes would come into the enterprise platform and be authenticated and authorized. Let's first explain which actors are involved here. We first have the client on the left side. The client is going to be either a user interface client or the Kubernetes command line tool. We have the UCP controller, which is the main API entry point for the enterprise platform. It's a component running on a container. It's just a standard Go binary. We have our own OpenID Connect provider. Now that provider has its own set of users and teams and manages external identities. It connects to potential third-party directory services such as LDAP or Active Directory to sync users from there. And we also have the Kubernetes API server, which is the entry point for Kubernetes workloads themselves. So when a request comes in from the client, it is either issued with a session token in its authorization header or with a client certificate as part of the TLS handshake. Regardless of which one it is, the UCP controller will authenticate the user using the OpenID Connect provider and exchange the session token with an identity token, which maps to the user. The UCP controller would then replace that identity token in the header of the request and forward that request to the Kubernetes API server. So the request comes into the Kubernetes API server with a JWT token that holds the identity of the user that issued this request, regardless of which session was originally provisioned. So Kubernetes would be configured to use the built-in OpenID Connect plugin to validate that JWT token was signed by the OpenID Connect provider that's part of the EE platform. And when that step passes, Kubernetes will be aware of the username of the user that was just authenticated. At that point, we move on to the authorization part, and Kubernetes API server will be configured with a standard webhook authorization plugin to contact the UCP controller component and request whether the specific user is allowed to perform the operation that was requested. The UCP controller is where the entire authorization logic for the enterprise platform lives, and it will perform a policy check over our role-based access control system. And if the request is deemed to be authorized for the user in question, the Kubernetes API server will respond back to the user with an OK statement. After that, we have a set of custom request initializers that will be applied on the pod before that pod is actually scheduled. And these would provide integration with Docker Content Trust and enforcement of policies around which teams have to sign a specific workload before it's provisioned production, and also enforcement of node selections for specific namespaces in Kubernetes. And that pretty much sums up our talk. So in summary, Docker will include an unmodified version of Kubernetes. There's topics on resource contention which are mitigated through workload separation for this version. And in Docker Enterprise Edition, authentication and authorization will be integrated through the standard plugin interfaces of Kubernetes. Thank you. All right, so we have a lot of time.
Yeah, so we have time for questions. I think there's 2 mics up there and 1 down here. If anyone has any questions you'd like us to address.
Yes, please.
You've mentioned mixed workloads. Can you give a real-life example that would warrant using this kind of setup?
Sure. So let's say you have an existing MTA deployment that you've spun up, and you have a number of workloads that you've deployed using Swarm, and those are running in your existing cluster. You've now upgraded to the latest version of Docker Enterprise Edition, which now has Kubernetes scheduling support. And you have some developers in your environment that are experimenting or using Kubernetes workloads as well. You may want to ensure that those new Kubernetes workloads don't end up landing on the same nodes as your existing MTA workloads. If your node is operating at the limit and you're essentially trying to do a consolidation play and kind of maximize the resources that you're squeezing onto each individual node, then as Alex mentioned, you can have scheduling contention between the orchestrators. And so those are the scenarios where you would want to do workload isolation and say this node is only for Swarm workloads, this node is only for Kubernetes workloads. But it's up to the operator or the administrator to decide which nodes they want to allocate. So essentially every node is capable of running all of the orchestrators, but you can choose which ones you want on which nodes. Go ahead.
Please. Sorry.
Yeah, so you guys demonstrated, I believe, using the stack file to create the custom resource definition for Kubernetes workloads to create the controllers.
Correct.
And then what I thought was really fascinating was you used the Docker CLI with just straight up Docker PS, which is an API that's traditionally used to examine just a single node. But you examined what technically would be the controller definitions of what would be like a Swarm task, like a single pod, and that's going to need to, I guess, go through the Kube API. There's no like task-specific observability things that are currently available in the Docker CLI for Swarm mode. So could you guys talk to like some of the decisions that you guys made in order to expose that UX?
Yeah, so specifically what we were demonstrating is a capability of the EE platform. I think you're referring to the CE platform. So if you're running a CE platform and you've enabled Swarm mode, that is correct. When you run Docker PS on a manager node, you are seeing just the workloads running on that individual node. One of the capabilities of the EE platform, because we also leverage the older Docker Swarm orchestrator as well, is that we also have accessibility to that full basic container API, if you will. Right? So Docker PS, when issued against a UCP, will actually see containers across the entire cluster.
Is that how that's been for a while?
Yes, it's been that way since UCP 1.0.
Oh, that's a really neat feature. Thank you. That clarifies things a lot.
Cool.
Yeah, that was,
You're welcome.
yeah.
Up there?
Okay, hi there. I have a question about networking. So will it be possible to expose a service via load balancer with a fixed IP address? I mean, not a randomly selected by you give me a subnet which I chose from an IP address, and I can directly assign that to the load balancer.
That part I'm not super familiar with. I don't know if you've played with that part. So this is basically ingress on the Kubernetes side.
In Kubernetes side, it's possible because it works on OpenStack and it works on Bluemix as well.
Yeah, I believe it should be possible. I'm not familiar with that specific part off the top of my head, unfortunately.
Thanks.
Maybe it should, yeah. Who's next?
We're going to go to the left.
Do you have a plan to open source the translator for translating Swarm API to Kubernetes API, or is it planned to be a proprietary software?
I think that's still under discussion. I don't think we've decided yet. Thank you for the vote.
So on a single node, would both Docker Swarm or the Swarm Orchestrator and the kubelet use the same Docker daemon, or at least the same container D instance?
Yes.
You're talking the CE? Yes.
Yeah, they would use the same Docker daemon.
Yeah, just a question. You mentioned in your slides that the beta will come to Mac and to Windows.
That's correct.
What about the Linux Docker C? In which Edge version we can go on it?
Excellent question. That's still under discussion as far as the best strategy for that. Right now, it's built on top of LinuxKit, which is not what we leverage on the Linux platform itself.
Okay.
So it's still being explored.
Okay, and just one more question. Will be the Kubernetes setup as easy as swarm --init? So kube --init?
Yeah, you won't even need to run that. I think it's going to essentially be a selector in the UI for the desktop editions.
Okay.
Once we've decided how we're going to do the Linux version, we'll have to figure out exactly how the UX works on that one.
Okay, thanks.
And then for the EE platform, it will be automatically enabled. Okay, go ahead.
If I already have a Kubernetes cluster and I want to use Docker stack deploy, but on my Kubernetes cluster, will it be available with Docker C and Docker EE? Because with the diagram, with the authentication on UCP, it seems that it was impossible.
I'm going to ask one of the guys from the Paris team if you know the answer to that one off the top of your head. I think it's still under discussion. Yeah, I think it's still under discussion. So as of right now, it would be built into the CE product, and it would be built into Docker Enterprise. We're not sure yet if it will be available generally for third-party Kubernetes deployments or your own homegrown Kubernetes deployment.
Are you thinking about adopting the CNI model also for Docker by, for example, writing a lib network wrapper, or also has an option to have a CNI plugin so you can really standardize on one networking model for Swarm and Kubernetes?
I don't think we have a firm decision on exactly how we're going to approach networking longer term. That's definitely an area that we're doing a lot of research on and exploring what the possibilities are. All right. Okay, well, thank you all. If there's no other questions.